All right, good morning, everyone. Welcome to our UTIG seminar this morning featuring one of our own. I'm delighted to introduce Chi Yan to speak to us today. Chi is a research associate who joined us over the summer. She was previously at the Carnegie Institution for Science, where she did a postdoctoral fellowship there, working on the magnetic field and geodynamo using numerical simulations. And prior to that, she did her PhD at Johns Hopkins University with Sabine Stanley. Again, doing dynamo simulations, but also including the Earth, Mars, and Saturn. So as part of this work, she's been involved with the Cassini data analysis, which was a mission around Saturn, and also InSight, which was a lander on Mars. So she has a great wealth of experience in planetary magnetic fields. So today she's going to be talking to us about Jupiter and Saturn with insights into Uranus and Neptune as well, very briefly, because that's what she's going to be focusing on for her work here at UTIG. And then prior to all this, she also did a master's in physics from the University of Toronto and a bachelor's degree in physics from Nanjing University. So she has a broad wealth of experience and expertise, and we're really delighted to welcome her today. So take it away.
Thanks so much, Krista, for your kind of introduction. Can people hear me okay here and online? Okay. All right. So today I'm very excited to talk to you about gas giant and planetary magnetic fields. And I'm hoping that by the end of the talk, you're going to grow some love for gas giants in our own solar system, and maybe also some love for planetary magnetic fields as well. Okay. So planetary magnetic fields, why do we care about them anyways? Okay, so in this scenario, we care because it is an essential building block for creating a habitable world. In this cartoon, that what we are seeing here is that with solar wind, there is a bunch of high energetic particles that is sweeping to Earth along with the solar wind. But with our own geomagnetic field, they divert these high energetic particles and then divert them to the polar region and create the wonderful aurora, which is where these high energetic particles interact with the upper atmosphere. Okay, and it just so happens that this year is the most active year of solar activity in the 11-year cycle. And believe it or not, you can see aurora from your balcony. All right, it's hard for me to believe as well at the first place. But apparently you can watch aurora from Central Texas. And this is a very beautiful picture in May that is taken, that I had copied over from CBS Austin. And if you look closely, there's a dog. Where's the pointer? There's a dog here, and then there's this beautiful medal here, and it kind of looks like a Stranger Things theme. So my favorite picture so far. And if you missed the May aurora, here are some more from just a week ago. So, and I was just proposing this idea, if we have a big enough group that are interested in aurora watching, maybe we can go on a field trip to some rural areas in Central Austin and see them in the later half of the year. Yeah, okay, so that's all the nice pictures I have. Okay, so for someone like me, I am interested in planetary magnetic fields because it can tell us a great deal about a planet's interior, which arguably is not directly measurable with instruments. And this is because planetary magnetic fields, they are generated in a planet's deep interior where there are electrically conducting fluids. They convect very vigorously. And with the planet's rotation, they form these complex helices, which are turned out to be very beneficial for generating magnetic fields. And then these magnetic fields then extend beyond a planet's surface and be made observable by different instruments. And also just before that, we can also use planetary magnetism, for example, from Jupiter's magnetic field. We can also study its satellite Europa with the Europa Clipper mission. When it gets there, hopefully in 5 years, we can study different properties in the subsurface ocean through this induced magnetic field with interactions with Jupiter's magnetic field. Okay, so here are some ways, different ways that we can measure a planet's magnetic field. First, we can send space mission to these different fields. Here is a brief table that some kind of summarizes different space missions that have been sent to the planets and get detected magnetic fields. And if we have a rocky planet, then we can also have the magnetic field be frozen into the crustal rocks as soon as these rocks cool down below their Curie temperatures. Okay, and this is then they can be analyzed in the magnetic labs. Okay, but notice that this is applicable to terrestrial planet or terrestrial satellites only. Okay, and then here's a table of different samples that we have collected. So there are Apollo samples from the moon, and then we have some meteorite from Mars and Vesta, which is an asteroid. We had a meteorite from Vesta that get analyzed, and it proved there are crustal magnetism in Vesta. For a past dynamo action. Okay, the third is really special. So if you're lucky enough to live on one that has an active dynamo, has a planetary magnetic field, then you can A, build magnetic observatories all over the planet. B, you can also send out different cruises to record the magnetic field, geomagnetic field. I will say maybe the only other planet that we have ever had a magnetic observatory is Mars, where we had the InSight, has a magnetometer, recorded a very substantial magnetic signature in the area it landed. Yeah. Okay. Here's a trivia question. Okay. Some of you might have seen this before. So how many active, and notice planetary dynamos, do you think are in the solar system? And the definition for an active dynamo is where a planetary magnetic field can maintain itself through a self-sustaining process. Because we're talking about planetary, so sun, our own sun, it is a dynamo, but we're not considering that in this question. Okay, so if you're ready, shout out answers, shout out numbers. Good. I hear 6, 8, 7. Yeah. Do I see a 4 or 5? Yeah, yeah. Okay. So 6 is the answer. Okay. Huh? Okay, get to that in a second. Okay. So so we have the planetary here. So if we're considering the planets, 8 planets in our solar system, then they are the 2 terrestrial planets, Mercury and our own Earth, and then 2 gas giants, Jupiter and Saturn, which we're going to talk about, and then also the ice giants. What about Ganymede? Or 7? So 7 can also be the correct answer. Okay. So Ganymede is Jupiter's largest moon. It amazingly also have a dynamo action. I think it was detected by Galileo, and then we have limited information about Ganymede, so other than its dipole component. So yeah, so 6 or 7 are both the correct answers. Yeah. Okay. So there are also many planetary dynamos in the past too. For example, it may be some people's favorite planet, Mars, also has a past dynamo action. And there are a lot of interesting problems with Mars Asian dynamo. And I think Doug is an expert at UTIG who has studied about Mars dynamo a lot. And then there's also our own moon. So we had analysis from Apollo samples that has proven that Earth's moon used to have an active dynamo, which is also surprising given its smaller size. And then there's Vista, we talked a little bit about before. And then Venus is the only planet in our own solar system that doesn't have a present-day dynamo. We don't know about its past because the surface of Venus is really hot. So people think the rocks are too hot to record the magnetic field if there were any in the past. But there are also arguments about Venus surface rocks that some rocks may be have a higher Curie temperature that might be able to record the magnetism in the past. So I think there are like mission proposals saying that we should go to Venus and say collect like some rock samples, something like that. I'm not very, very sure about that. Okay. All right. So here is, so what we are looking here is those active planetary dynamos and what their magnetic fields look like. And I want to say for those active dynamos, we have a zoo of planetary magnetic fields. And the way to read these magnetic field pictures is you would imagine that the magnetic field lines are coming out from these red contours and then going into those blue contours. Okay, so this is, for example, the Earth. Then we have like field lines going on here. And then for Saturn, then we have like field lines going here. Okay, so by very roughly eyeballing these magnetic fields, we can roughly categorize them into 2 different groups. One is what we called dipolar dominated fields. That is, you can basically replace the magnetic field by putting a bar magnet in the center, maybe like with different direction and that. So by this principle, then we can categorize Mercury, Earth, Jupiter, and Saturn into the same category, which is the dipolar dominated fields. And then for Uranus and Neptune, we can't put a single bar magnet, so that they are the multipolar fields. They're non-dipolar dominated. Okay. And here's Ganymede again. I'm not plotting its radiomagnetic field here. Yeah. Okay. So before we take a trip to the gas giants, we need some gears. Okay. The first gear that I want to introduce to you guys is the Gauss coefficients, which are something that we deal with on a daily basis. So just like the gravity field, the potential of the magnetic field can be expressed in a series of spherical harmonic expansions. In numerical simulations, we often have a maximum truncated number of the maximum spherical harmonic degrees. And what you see here, the GLM and HLM are called Gauss coefficients. Okay, they are the coefficients in front of cosine and the sines. The L's represents the spherical harmonic degrees, and the M's represents the spherical harmonic orders. And the PLM here is the good old Legendre polynomials. So starting with the largest three features in Gauss coefficients, and there are a specific pattern that I want to introduce, which is the axisymmetric pattern. So when we set the spherical harmonic degree to be 0, that would produce an axisymmetric field. So that means they are invariant in the longitudinal direction. So the three biggest components are the dipole field, and then the quadrupole field, and then the octupole field. Okay, so with these Gauss coefficients, we can basically reproduce what any planetary magnetic field. Okay, so here is an example that how we can reproduce the geomagnetic field at Earth's surface in the year of 2015. The data is from the I think it's International Geomag Reference Field. Yeah, so basically, this is how you can reproduce the geomagnetic field. And one thing you'll notice that is from approximately degree equals 5, you don't see any like big changes in the field. And that is because as you go to higher and higher spherical harmonic degrees, they represent smaller and smaller spatial features. So the largest feature are those spherical harmonic degrees where there are that are smaller. Okay, and here is more mass. This is our solved governing equations of people doing dynamo theory or dynamo simulations. So we basically solve how the fluid evolves, how the fluid moves in, take Earth, for example, how the fluid moves in the outer core shell. The first equation is the Navier-Stokes equation or the momentum equation, and it's it's pretty much the same of the same equation that you'll see in atmospheric or oceanic sciences, except for this term, which is the Lorentz force. That is where the magnetic field comes in. And then how the magnetic field behaves is governed by this magnetic induction equation. This is derived from the Maxwell set of equations, not functions. And then we have a creation of the field, and then the field is also slowly diffusing away. And then we close the whole system with a temperature equation, okay, or the energy equation you might hear in some other places, okay. So we solve fluid motions and magnetic fields, how they evolve in time. And just one more, this is how the dynamo simulations would work. So first of all, we would have some input, some initial conditions of the velocity field, the magnetic field, and the temperature field. We feed them into the set of equations with preferred prescribed boundary conditions for all of the fields. And we will also think about what are some specific interior structures that we would like to input into this dynamo simulation. And then we solved the whole system and got a set of output of velocity field, magnetic field, and temperature. This is how the whole system is evolved in time. And at some point, we feel like there's enough of time steps we have run. The field has been satisfactorily equilibrated. And then we will be comparing our output of the magnetic field with what's observed in planets. And with this process, we're hoping that we can get some information or interpretation of what might be going on in a planet's interior. And just one more before we actually go to look at gas giants. We have been, so like many studies, we started with Earth, okay? So similarly, dynamo models also started with geodynamo models. And we have been doing a pretty good job, and the geodynamo models have been also turned out to be quite good for a standard case to test as well. So geodynamo models have been able to reproduce a lot of salient features concerning the geomagnetic field. It has been producing the dipole dominance, its secular variation as well, which is not shown here in the figure, but it's also some dynamo models have been put output reversals as well. So there is even the paper that categorized what would be an Earth-like geodynamo. So we have been doing a fairly good job with geodynamo models. And now let's take a trip to Saturn. Okay, so Saturn's magnetic field is truly amazing. We have been sending out space missions to visit this planet. And you can see from this timeline that it is found to be more and more axisymmetric with space missions that are more and more designed to be exquisite. And if you think about the amount of precision in that, the dipole tilt would, it would rotate, and then it would create this surface area. So by having a dipole tilt decreased from 2 degrees to this 0.06 degrees, and then I think I missed another measurement, which is I think 0.001 degree. That's 6 orders of magnitude in terms of the surface area that the dipole tilt has been confined, because it's proportional to the degrees, the square of the degree, right? So that means the magnetic axis is perfectly aligned with its rotational axis. You cannot find any dipole tilt, any angle between the rotational axis and the magnetic axis. And this is the first and foremost dramatic feature of Saturn's field. And I love being dramatic about this here. I would say it's problematic because it obviously violates this famous anti-dynamo theorem, which is called Collins theorem, that basically states that you cannot maintain an axis-symmetric magnetic field through dynamo action. And worry not, we're not violating Collins theorem here. So what Collins theorem applies is really in the interior of the dynamo region. More specifically, it's applied to where dynamo or magnetic field is generated. But what Cassini or previous missions visited Saturn observed is its surface field. So if we have some kind of mechanism that is can act on top of the dynamo, region, and then can shear out those non-axis symmetric magnetic fields, then we would have a magnetic field that appears axisymmetric at the surface, and that would not be a big problem. Okay. So we're gonna carry this, and we'll show that in the later slides we can, in fact, get to that. Okay. So now what I'm showing you is a power spectrum, and we'll be seeing that a lot in the later slides. So what we're basically doing is we take this map of the radiomagnetic field of Saturn, and then we decompose them into different spherical harmonic degrees, and then we calculate how much power is in each and every of the spherical harmonic degrees. Okay, what's special in this power spectrum is that, and you don't see that in any other power spectrum of planetary magnetic fields, is that we can also show the signs of these power spectrum. And that is also because it's extremely axisymmetric. So essentially, what you have for this different degrees is only the zonal components, okay? So then with the zonal components, you can say if I have a positive dipole, axisymmetric dipole, or a negative axisymmetric dipole. So here I have the solid pentagram, meaning the positive sign, and then the open pentagram, meaning the negative sign. And why that matters is that it would affect the resulting magnetic field morphology. So here is an example. If I combine a positive dipole and a positive octopole, and we can do with by eyeballing it, right? So you will have, if we put these two together, you would end up getting a concentrated field in the polar region, right? And then a field that is weakened in the equatorial region. So here is what it's gonna look like with a very extreme case, okay, very high octopole. Alternatively, if you have a negative sign, okay, then you would have a concentrated magnetic fields near the equatorial region, and then the polar regions would be weakened, like here. Okay, so Saturn has a positive octopole. That means its polar magnetic field are strong. All right. The second feature that I would argue is that it has an excessive power in the octopole. And this has something to do with by looking at the lowest, so-called lowest power spectrum. So when we are away from the dynamo source region, and when you look at different spherical harmonics, so the field, the magnetic energy would decrease exponentially with respect to a component that is 2L+4. That means the higher spherical harmonic degrees would decrease much, much faster than the lower spherical harmonic degrees. But here we are seeing that the octopole has a much higher energy distribution than the quadrupole, which is degree 2. And this is really abnormal. Following the very same rationale, if we put some straight lines in this power spectrum, you'll notice that there seems to be a slope that is very sharp in the lower degrees, and then a slope that is shallower in the higher degrees. And that is by the same rule. So some people have suggested that this shallower slope may be caused by a dynamo that is maybe closer to Saturn's surface. Therefore, they might be able to generating this high power in the higher spherical harmonic degrees. And the last feature is its temporal behavior. So people in the Cassini mission have found that how the Saturn's magnetic field is not changing at all in the temporal behavior. So it's not changing at all with time. The secular variation of Saturn's magnetic field is at least one order of magnitude that's slower than the geomagnetic secular variation. So with all of these weird features, we think there must be something going on in Saturn's deep interior that's causing this, okay? And it's not a standard dynamo simulation that we would see on a daily basis. Okay, so the first ingredient that might help resolve this issue is what's called a helium insoluble layer. It's not a new concept. It is proposed by Dave Stevenson in 1980 and 1982. So what would be going on basically is when hydrogen, the most abundant component in gas giants, when hydrogen undergoes extreme pressures, it transitions from a molecular state to a metallic state. And when this transition happens, helium is not happy about it. it decides it's going to be insoluble or immiscible from the metallic hydrogen. So they started, so if we look at Saturn's adiabat here, it started to become immiscible with the metallic hydrogen from a pressure that's around 1 megabar pressure. And it starts this raining process. And then at a higher pressure around here, it becomes miscible with metallic hydrogen again. So then we have this, constant pressure range where helium would be constantly raining out from the metallic hydrogen. So here I have this illustration where this would be the thick atmosphere of Saturn, and then this green mint area would be the area where helium is raining out. And then the deep region would be the metallic hydrogen where dynamo happens, okay? So this helium insoluble layer, because it's raining out, it has this compositional gradient in this layer that is stable to convection. And with this, so it's not, there is no convection going on in this helium rainout layer, okay? And with that, there might be differential rotation happening in the helium rainout layer, and that can act to shear out the non-axisymmetric field that might be generating in the dynamo region, and so that the surface field would appear axisymmetric. Some ways to induce differential rotation in the helium rainout layer are through variable heat flux perturbations. So there is this idea of that from solar installation, you could possibly have a hot equator and colder poles, okay? And there are also some other ways, that is through atmospheric convection, that would also result in a hot equator here and relatively colder poles here. So that would induce a negative Y20 spherical harmonic pattern. So we put these two ingredients together and then see what's happening in the resulting magnetic field morphology. Okay, so I want to go quickly by this. So first of all, we tried a standard case, okay? So we didn't put any special ingredient, didn't put any helium rainout layer or variable heat flux pattern on it. So what happens is that it's the same model, but then we embedded the dynamo surface at different depths. Okay, so the first one, so first we try it at 55, which is relatively deep dynamo surface at around 55 of Saturn's radii. You can see that it matches the higher spherical harmonic degrees relatively well, but it does a very poor job here. If we decided to match the largest feature here, then we move up this dynamo surface to about 85% of Saturn's radius. But then you see it has an astonishingly high power that is nowhere near Saturn-like, okay? So then we tried the helium insoluble layer. So we implement a helium insoluble layer that's about 20% of Saturn's radius. And this starts to give a zigzag feature, which has turned out to be a, which has turned out to be a very specific feature related to the stable layers. So we are doing a good job matching this, but then the important thing is that we're not matching the large scale morphology. So then we tried to add the heat flux pattern, okay? So this seems to creating the correct differential rotation in the stable layer, and it gives us this dipole to octopole both in correct signs and seems to be in the correct power range. It does lose some features in the higher spherical harmonic degrees. We then modulate this heat flux pattern to be more a little bit more sophisticated, and then it seems this is our like best model so far, but it's not the best. So it seems to be capturing the large scale features and also the zigzagging and the power in the higher spherical harmonic degrees. I will say that it doesn't do a very good job in the degree 5, and this is still ongoing work to reproduce a more Saturn-like magnetic field. Okay, so then here I'm going to show you how the magnetic field is actually getting axis symmetrized. So what I'm showing on the right-hand side is a interior sketch. So we're going to see radial magnetic field from the bottom of the helium insoluble layer all the way to the top of the helium insoluble layer. So you can see that right now at the bottom of the stable layer, it's quite non-axis symmetric. There's a lot of non-axis symmetry in this field. But as we go through the stable layer, it becomes more and more axis symmetric. Okay, so, okay, these non-axis symmetries are fantastic. And where do we find them? Okay, so here, what we're comparing is our most axis symmetric case to a standard case. And their non-axis symmetries are at the bottom panel. Okay, so by comparing them, you can see that the non-axis symmetric field are really in the polar regions. Okay, and this is where we get the least data with Cassini mission. Okay, so see, this is the blue lines are the grand finale orbits, and they are far, far away from the polar regions. So if there were any non-axis symmetry in Saturn's magnetic field, the best chance is that they are located in the polar regions. We did a synthetic study where we have our modeled field and then have a Cassini grand finale orbit orbiting this Fox planet. And we didn't see any non-axis symmetries with our modeled field as well. Yeah. Okay. So much about Saturn, and what about Jupiter? Okay. So I want to say that our view has been very greatly changed by the Juno mission. So before Juno mission, we have been viewing Jupiter, and of course, it's in terms of its magnetic field, we have been viewing Jupiter as an Earth analog. And there are a very a good amount of reasons for why we're doing this. So previously, all those Pioneer 10, 11, Voyager, they were able to characterize Jupiter's magnetic field down to spherical harmonic degree 3. And this is what Jupiter's field looked like at that time, okay? So if you view Earth's magnetic field and Jupiter's magnetic field, they are really alike. They even share the same dipole tilt axis. They're both about 11 degrees tilted, okay? And beyond that, Jupiter-like interior profiles in dynamo simulations, they also produce this type of Jupiter magnetic field that is dipolar dominated and to some degree tilted. So we're happy back then, okay? But then after Juno, since the first 9 orbit of prime mission in Juno, we have found that Jupiter's magnetic field is nowhere where we imagined, okay? So what instead is a very perturbing, not that perturbing, but a little bit perturbing spot near the equator, and this huge magnetic flux pattern in the northern hemisphere. So there are actually a lot more differences than what was expected. So we're seeing Earth's magnetic field and Jupiter's magnetic field again. It's somewhat perturbing now, comparing for me plotting Earth as the same size as Jupiter, where in fact you can fit 10 Earths into this great red spot, right? So they are very, very different. And okay, let me just go back one slide again. So this is what their radiomagnetic field look like. What I'm going to do next is to take out their largest feature, to take out their dipole component and look at the rest of the field at their relative dynamo surface, okay? So for Earth, this is at the core mantle boundary, which is about 55% of Earth's radius. For Jupiter, it's less certain because there is no physical boundary between a dynamo surface and its upper atmosphere. We choose like 85 to 90% of Jupiter's radius by the evaluation of the magnetic Reynolds number. Okay, so they are plotted at their relatively considering dynamo surfaces. And what you'll notice that is excluding the dipole, okay, the rest of the field is more or less uniformly distributed at Earth's core mantle boundary. But it's not the same case for Jupiter, okay? So except this little spot that can be considered in the southern hemisphere, there really isn't a lot of the magnetic field in the southern hemisphere. Whereas in the northern hemisphere, there's still this big red flux, okay? And in the dynamo community or in the planetary community, we call this great blue spot in resonance, in analogy to the great red spot. But so here is a few disclaimers about this great blue spot. First, it's not blue. It's just so that we choose a color map, okay? We choose a color map that shows this blue spot. And second, it's not to be meant to be comparing to the great red spot. They're probably very different, and they are, I want to say, tens of thousands kilometers away. So it's not that they are linked by some mechanism or what. So the great red spot is not supposed to be the mechanism that's causing this great blue spot. Okay, enough spots. Okay. So the rest of the field, hopefully I've convinced you, it's really hemispheric. It's really concentrated in the northern hemisphere, okay? We are not seeing this kind of hemispheric magnetic field feature anywhere else, except maybe the ancient Mars crustal magnetism, okay? Leave it like that. I want to say here that for the previous models that we have seen, especially for the Saturn models, what haven't been considered is that, especially with giant planets, their electrical conductivity is not a perfect constant, okay? So when molecular hydrogen undergoes the extreme pressure and becomes metallic, it is not like a step function. It's not a sharp transition, but rather it is a smooth transition, okay? So from this figure, what I'm showing here is that here are what we think is the electrical conductivity profiles with respect to the radius. What I hope this looks like is a purple, but now it looks like a black line, is Jupiter's electrical conductivity profile. And the orange line here is Saturn. Okay, so you can see that Saturn is a bit more dramatic. The conductivity only starts to be appreciable at around 62% of Saturn's radius. And you have maybe a good amount all the way to like 80% of its radius. Whereas for Jupiter, it's relatively good. The conductivity doesn't drop until around 90% of Jupiter's radius. Okay, So we take this conductivity profile and then we implement it into our dynamo simulations with Jupiter-like interior profiles. And what we got is instead a multipolar magnetic field, not a dipolar dominated field. We put this into, we put this Saturn-like electrical conductivity profile into the Saturn profile. It also produces this non-dipolar dominated magnetic field. This is just a snapshot, so it's not always like that. It's not always like hemispheric like this, just a disclaimer here. Okay. So what I think might be happening is that you might need a helium insoluble layer again. So here is the figure that we see before. So I talked about Saturn's, why Saturn helium insoluble layer, and I didn't talk about Jupiter. So Jupiter may have a thin stable layer, a thin helium insoluble layer that is stable to convection at the present day. It might be much, much thinner than what Saturn has. Okay, this is because Jupiter originated from a much warmer state initially when they formed, so that it enters this hydrogen-helium immiscibility region much later, at a much later stage. So here's the idea of the helium insoluble layer, and we put a thin helium insoluble layer into the model, into the same model, and here it produces a dipolar dominated magnetic field as a result. Okay. So what I think might be happening is, oh, apologies for this not very good color on the screen, but hopefully you'll see like the color, the yellow color, which means high kinetic energy, is concentrated here and here. Okay, so this is what we're looking here is basically the kinetic power spectrum with respect to different radius and with respect to different spherical harmonic degrees. Okay. So this is when we have a Jupiter-like interior profile without a helium insoluble layer. And here is what when we had this helium insoluble layer. So what seems to be working is that this helium layer seems to be able to push back the kinetic field, push back the flows into the deeper region of Jupiter. And it separates the dynamics between the semiconducting layer where the conductivity is relatively low and where the dynamo is really happening. Okay. Just want to quickly check what time. Okay. Have a few minutes. Okay. All right. So where else do we have variable conductivity profile? Uranus and Jupiter. No, Uranus and Neptune. Okay. So here is the ab initio and high temperature, high pressure experiments on the water in ice giants. And they are also the conductivity of these two ice giant planets are also varying with radius, with depths. Okay, so we can also use this to study Uranus and Neptune. And I also want to quickly point out that their power spectrum for the ice giants are really strange. Okay, so they would be this blue triangle and the cyan triangle here. They're really high up for so comparing to the dipole, the quadrupole and octupole have really high energy. And this is very abnormal due to the power spectrum that we just discussed, though they're not supposed to behave like this, right? And we also observe this like high power in the spherical harmonic order that equals to 1. And there are some special features that I think this, yeah. that I think this M1 feature is really, really special, and it seems to be consistent. We see them in both planets. And okay, so if I go back to this plot and that plot, do you notice any difference in these two plots? So, okay, so the Saturn is not in here. And yeah, it's understandable and correct, is because we don't have any M non-zero components. Okay, so that's why Saturn is not there. And here is just something that I did over the summer, that we implemented this variable conductivity profile, and one model seems to be producing this M1 feature constantly. And I have a one-liner for why we should be going to Uranus. So Uranus might be the only other planet where we could observe secular variation that is originated from dynamo process. Okay. I think I'm very, very about time there, but okay. So I want to show you this picture. Okay. All is amazing and seems to be solving the problems, but the gas giants have fluffy cores. Here's my dog there. She's fluffy, but rest assured, I'm not sending her to the cores of the giant planets. If there is such a chance, I'll beat her to it. Right. Equivalently, you might hear this as dilute cores or fuzzy cores. They're all the same thing. So basically, what's happening is that by by ring seismology and gravity measurements that's performed by Juno and Cassini missions, they have found that the deep interior of the gas giants are stably stratified. So that's where the dilute core comes from. So the heavy element, instead of a sharp boundary between the rocky inner core, instead it's a composition distribution from the center of the core to all the way to about 60% of their radius. And this is really a challenge or a crisis for gas giant dynamos, okay? Why is that? It's because, as we just mentioned, Saturn's conductivity starts to drop at 62% of Saturn's radius. And if you have 60% of Saturn's radius being stably stratified, then that leaves like 2% of the radius to have dynamo action, which is very, very difficult. It's less of a challenge for Jupiter, where we would have about 20 to 30%. I put RS here, which should really be RJ, which is Jupiter's radius. So we have a decent room for Jupiter dynamo to happen. But even so, such a geometry would almost lead to multipolar field instead of dipolar dominated fields. So this is dilute cores really pose a challenge for the gas giant dynamos. And what might be the rescue to the gas giant dynamos is the double diffusive convection, which I probably don't have a lot of time to talk about, but it might be resolving this dilemma. And I'll just leave it here. And I think gas giants, they're wonderfully weird planets from a dynamo perspective, and happy to take any questions.
Thank you, Chief, for a fascinating seminar. We have some time for questions, but because it's a little bit short, I wanted to prioritize if there was any students, early career folks that would like to get the microphone first.
So you have this kind of I can't remember what you called it, the the rainy section. And you have to have a certain thickness of that to propagate through to get your dipolar field. Does that constraint of the thickness of that region kind of feed into atmospheric modeling of these planets and things like that?
Like the thickness of the helium ring-out layer to the atmospheric modeling?
Yeah.
I think what I am used to have is to have the atmospheric modeling to have a feedback on our modeling. But what we can say about this is it probably can act as maybe like a boundary condition for the atmospheric modeling. Yeah.
Thank you very much. Oh gosh.
That's a
Wait, when?
long
You.
story.
Hi, Chi. That was really interesting, and I don't think about this stuff a lot. I think my question does link to Alice's well, related to these kind of, I guess, atmospheric processes in the gas giants. I'm curious, I guess maybe naively, we'll see. I might think that processes going on kind of within like the gas layer, outer gas layers of these planets might change somewhat rapidly, even on like human timescales or observational timescales. So I'm curious if you can comment on the observations we have of the dynamos, which are from the exterior. How much might we expect those to be representative of a given point in time versus if we went back now, would we see the same thing? And does that make sense? Like how much is the atmosphere maybe changing and affecting our observations of the dynamo at a given moment?
They are very different. They're in very different timescales. So magnetic field timescales, as I was just talking to Ben about it, is like so take Earth, for example. Their timescale is about hundreds of thousands of years. So a very, very long timescale considering the atmospheric changes. I don't remember what would be for the Jupiter's atmosphere, but I would bet that's also like relatively small to Jupiter's magnetic field changes. And the way to transfer like the magnetic timescale is to look at the length scale for the dynamo region, and then there's also the component of the magnetic diffusivity. So taking that into account, I think Jupiter's magnetic time scale is going to be much longer than what's happening on Earth. Yeah, so it's a long time. There are studies about like secular variation for Jupiter's magnetic field, and that's a very short time as well. I think it's about like 50 to 60 years, and that's looking at data from previous missions in like Pioneer, the 10, 11, Voyager, those data, and to compare it to the Juno data. So that's like around decades. So studies also have shown that this secular variation is possibly not due to dynamo action itself, but rather than it's like the advection of the zonal winds that happens near the boundary of the dynamo region. So yeah, so that's something. Yeah.
Thank you.
Geez, thanks for the talk. That was very clear. I learned a lot. So my question is, you mentioned degree for Saturn. You mentioned excess power at L equal to 3.
Yep. Yep.
But seems like the most discrepancy was degree 5. I know it's ongoing research probably, but do you have any idea like how should I interpret the significance of that degree 5?
That's a very good question. So yeah, degree 5 is where we do the worst, right? But so here's a few things. One, degree 3 is, I would still consider it being more of a discrepancy than degree 5 because it has, because A is that the degree 3 has a more like a larger feature, right? When you consider like higher and higher degrees, those features go smaller. So degree 3 is still a larger feature than degree 5, and because of its a higher power, so you will see more of the degree 3. So it's important to match the degree 3. The reason why we're not matching the degree 5 might be that one is that there might be this like shallower dynamo that's operating. So then you would separate the deep dynamo and the shallow dynamo. So then it wouldn't be surprising that the degree 5 would be small. And that's something ongoing work. And another guess that I would take is that instead of this imposed variable heat flux pattern, what I haven't tried, and I think some other dynamo studies have tried, is to take the zonal winds that's observed on Saturn and take that as a velocity or a thermal boundary condition onto the dynamo. And I think if I remember correctly, they've been producing this low degree in the low power in the degree 5 that pretty well. So that might be something else, which is the reason that we are not doing a good job in the degree 5.
Right, we are a little bit past time, so I will just note that there are additional opportunities to talk with Chi. For example, you could join us for lunch. We're going to meet at 11:45 in the lobby. There's also some slots available in her schedule this afternoon that you could sign up for. And we'll also be going to Asa Works this afternoon around 5, or you could just email her or stop by her office, which is in Torsten's pod. So I wanted to say thank you again, Chi, for a great talk.
Thank you guys so much.